Hello everyone! Hey Debunked! Oh, you are early, my man. You are very early. Good stuff, dude. Let's get that chat going. There we go. Yeah, so today we are going to do even more array marching. And I'm very excited for this because I did actually find one good algorithm that we are probably going to use in order to actually finish this array marcher. And I have that all prepared, of course. This is just a random new tab. Don't know what that's about. This, however, where do I have it? It's right here. Here it is. So in this paper, a fast voxel traversal algorithm for ray tracing. And well, let's go down here, and basically it says here we have a new algorithm, right? That is very much specifically made for voxel tracing. And this is basically what it does in 2D. So let us actually just run through this, because it is actually very simple. Like, this is the entire explanation. Like, that's it. That's it. Just a couple of paragraphs. That's just insane. So, to correctly traverse the grid, a traversal algorithm must visit the voxels A, B, C, D, E, F, G, and H in that order. So, the equation of the ray is U plus TV for t equals greater or equal to 0. The new traversal algorithm breaks down the ray into intervals of t, each of which spans one voxel. We start at the origin and visit each of these voxels in interval order. Debunked, I have a question. Did you think about using a 3D texture for your chunks or a voxel? Yes, I did, but what I want to say, well, I suppose, actually I did think about that, but back when I did think about that, I was convincing myself that I wanted to make an octree, and a 3D texture with just every single voxel in it, it's very wasteful when you are using a octree, because an octree will actually save you some space as well. It won't only make your traversal faster, but it will also save you some space. Now I am doing it a bit differently, and I guess I could use a 3D texture. But I'm not sure if that will necessarily help me too much, as opposed to just using just a normal array, since, well, we're not using GLSL anyway, we're using OpenGL. So I suppose that just using a normal buffer will give us the exact same speeds. But yeah, if you're using GLSL, doing this exact same method, then a 3D texture makes total sense. Absolutely. The traversal algorithm consists of two phases, initialization and incremental traversal. The initialization phase begins by identifying the voxels in which the array origin U is found. So for us, that is just extremely easy, right? It's very, very easy. We divide by 32, and then we find a chunk, and that is basically our quote-unquote voxel to begin with. And then if there are any voxels in the chunk, then we go down in levels of detail, basically. Okay, go down in what do you call it? Like in definition? I don't know. If the ray origin is outside of the grid, we find the point in which the ray enters the grid and take the adjacent voxel. So that makes sense, right? So if we start here and we go up, then we basically just take voxel A to start off with. The integer variables x and y are initialized to the starting voxel coordinates. Right, makes sense. In addition, variables step x and step y are initialized to either 1 or -1, indicating whether x and y are incremented or decremented as the array crosses the boundary voxels. So that is basically just the sign of your direction. So in this case, in this picture, we are going to the top right, which means we are incrementing x in a positive direction, and we are incrementing y in a positive direction. we went this way, if we went down like into this paragraph, then x would still be positive, but the step y would be negative. So quite simple. This is determined by the sign of x and y in the components of t. Yeah, so quite basic. Next, we determine the value of t at which the array crosses the first vertical voxel boundary and store it in variable t max x. So basically, we are going to increment t until right this point when we first reach the x boundary here. And that will be t max x. We perform a similar computation in y and store the result in t max y. So we will also find this one for t max I, for where the array first crosses a border in the y direction. So we'll have these two t's, and now we basically just pick the smallest one, I believe. The minimum of these two values will indicate how much we can travel along the array and still remain in the current voxel. Yeah. So in this case, that would be t max x. Finally, we compute t delta x and t delta y. T delta x indicates how far along the array we must move in units of t for the horizontal component of such a movement to equal the width of the voxel. Right. Wait, let me reread that, because now I don't exactly know what they mean by this. Finally, we compute t delta x. T delta x indicates how far along the array we must move for the horizontal component of such a movement to equal the width of the voxel. So I guess t delta x would be like this much, right? Because then we would be at approximately the same position in x, and then that would also get us there, get us there, get us there, get us there, right? Because it's a line, so it's linear, so that will always be the same relative x position in each voxel. That makes sense. That makes sense. Similarly, we store the t delta y, the amount of movement along the array, which has a vertical component equal to the height of the voxel. The incremental phase of the traversal algorithm is very simple. The basic loop is outlined below. Yeah, so basically, we just loop through this. If, and then t max x is smaller than t max y. So in the case that we cross x before we cross y, then we say t max x equals t max x plus t delta x, which means that we are just going to add t delta x, which means that we are going to end up here. Is that what I'm getting here? And then x equals x plus step x. Yeah, so we are just going to move one to the right, in this case, one voxel. Why does t max x increment by t delta x? I'm not entirely sure, actually. Hey, Jacob. Welcome, welcome. Else, so if we cross y before we cross x, then t max y equals t max y plus t delta y, y equals y plus step y, and then we just loop to the next voxel. In 3D, it's basically exactly the same thing, only we now also have to check for z. So we get a couple of extra cases here. Double equals just out z. Honestly, not entirely sure. So if the x is smaller than... Oh yeah, okay, so we have to do these, yeah. If y is just out y or x is just out x. Not entirely sure what they mean by that. I didn't have that in the 2D case. We loop until either we find a voxel with a non-empty object list or we fall out of the end of the grid. Oh, okay. So basically this just indicates, okay, we are outside of the grid now. And so we should just return an empty array. Yeah, and then we just do that for 3D too. That makes sense. To correctly determine visibility, we must make sure that the closest intersection point... Yeah, okay, so this part doesn't even matter anymore, because here they have to check, okay, B is here in voxel C, but A is in the voxel above it. So we are first going to check voxel C, and then we are going to find B, so we find this intersection right here. But of course, there was an intersection earlier with the other object. For us, this just really doesn't matter, because every voxel just has exactly one object, so it's completely fine. Yeah, and that's basically it. It should be very, very fast. It is very clear what it does, which is nice, because what we have right now is actually... Wait, let's keep it actually on the screen. what we have right now, we did this weird intersection algorithm. I don't really understand how it works. It's not even this one though. Where is it? Oh, this one. Yeah, I'm not even sure how this one works. It looks very complicated. It looks like a lot of stuff is going on. We don't need any of this. So we're going to remove this again, like for the 5th time. And then we're going to switch to this new intersection algorithm. We have like 5 different ones now, but that's okay. Okay, let's get started then. And let's get started just by looking at what we already have. So, candy here is just get the camera direction. Yeah, that makes a little sense. X equals across, Y equals that. Yeah, so this is for the offset of the camera of every ray offset. Then we get the origin of the ray, and then we get the direction of the ray. Yeah, makes total sense. The position, the current position is just the origin. Then we have the chunk position as well. Yes, with vector 3i. Sure, yeah. So every time we just take our current position, our like floating point world position, divided by 32. Firstly, floor, of course, very important. I use this floor here because in the negative x and negative y, it will, if you just cast it to an integer, it will seal it. It'll take like minus 0.8 will be rounded up to 0 instead of rounded down to -1, which is why we use explicitly floor here. With the color, yeah, as long as color equals 0, meaning that we have not found the actual color yet. And of course, we will add some more nuance to this later, maybe with some with some transparency and stuff. And we don't quite want to do this, but for now, this is fine. Then we get the chunk at the current chunk position. Yeah, that's also fine. Do we even need to do that? No, I don't think we even need to do that. Yeah, we don't need to. You know what? I guess we do need the chunk right now because we don't have all the different levels of detail yet of our distance maps. So I suppose, yeah, we get the chunk. Then if chunk is null, then we have presumably reached the edge of our world. Therefore, we can just return our blue background color, whatever. Otherwise, we go through the voxels. So float t1 equals intersects that. Yeah, we don't really need that anymore. And we have the voxel position. Then we have this, that, yeah. Oh, here we have to get the distance. Voxel, yeah. Oh yeah, we worked on the actual distance last time. I think I'm actually going to remove that. Let's work on that first, then, I suppose. Because right now we have an actual distance map. But come to think of it, I don't really want a distance map. This is what I'm just quickly going to show you. Because this is an idea that I had this weekend. And I guess I didn't really show this yet. So right now what we have is, let's say we have our 2-dimensional chunk. And of course our 2-dimensional chunk is chopped up into little bits. And every little bit right now has a certain distance to the nearest actual voxel that is not empty. So this will be 1, this will be 2, this will be 1. It's 1 on the edges, right? Yeah, 1. Oh yeah, so all the edges had 1. Maybe there is an actual voxel here, so that will be 1. That'll be also 1 actually. 1, 1, 1, something like that. This actually can be 2. There we go. Something like that. Now, the thing is, right? The thing is, this is a lot of work to keep track of. Because of course, if this one turns into a 0, then we have to update that one, we have to update that one. I guess not that much more, but you get the idea. If it's a bigger map, we might have to update a bunch of them. Because if there's like a 3 and a 3 and a 3 here, then we have to update all of those as well. It's a bit of work. We don't really want that. We want the least amount of work as humanly possible. And what's more, I think we can do it just as efficiently in another way. What if instead of doing the actual distance map, we just have sort of flattened octree. That's kind of what I dubbed it. Not sure if it already exists or not, but this is what I came up with. So instead, we just take the octree approach, which is we just have zeros and ones in here. And a 0 means that this chunk, and I guess in the first level of detail, that would be a 2 by 2 by 2 chunk, little sub-chunk of voxels, 8 voxels in total, is empty. And a 1 means that there is at least one voxel in there, non-empty voxel. So if now you have an array that comes along this way, other color, oh, there we go, other color, maybe even red, but it comes this way, right? It finds this map voxel, super voxel. I don't really know how I should call this. Maybe this is a super voxel. Let's call it a super voxel. Super voxel. And that is somewhat clear, hopefully. It's 0, so we just continue on like nothing happened. And imagine these are like 2 by 2 by 2 voxels back together. So we basically move, if we just go completely horizontally, we move 2 at a time. So we get to this one, empty, so we move on. We get to this one, empty, we move on. We get to this one, it's not empty. There's at least one voxel in here. That means that we now have to check against 8 other voxels. Right, we have to check 8 voxels right here and see if we hit any one of them. If we do, well, and I say 8 voxels, but actually we don't even have to. If we're smart about this, we can actually know like the sub position that our array has, and we can just check this voxel. If it's empty or not. If it is empty, then we move on just 1. If that is empty, we move on 1 as well. At most, we are going to get 3 checks, I believe. 3 different voxel checks. If we like go totally diagonally like this, you get 3 voxel checks. Now let's say this last one is actually green, so there is a non-zero voxel in there, then we can just return green. Then we have traversed the entire, what should we call it? An entire chunk, which is 1, 2, 3, 4, 5, 6, 7, 8 voxels in size in this direction. We've only checked 1, 2, 3, 4, 5. So you know that's almost a 50% discount. If we had found this one earlier, let's say we found it already in here, then of course it would have been only 1, 2, 3 checks out of 8. Or I suppose you would have done 1, 2, 3, 4 checks. So 3 out of 4. So you do get quite a nice gain. The bigger you get, the bigger your gain will be. Right? Now imagine that we have another level of detail. So we go up 1 level. Now instead of it being like this, 4 by 4, we divide every side by 2. So it will only be 2 by 2. This one is 1, that is 1, that is 1, this one is 0, right? If we have the same map there. So now, if we come in here with our array, that's about where we were, right? I suppose we were here. We hit this even bigger super voxel and we see, okay, there's nothing inside of this entire area. So we just move on in one go. And then only when we get here do we start checking out the higher details. So we get back to this. So now we do the same thing. But there's only 1, 2, 3, 4. 1, 2. And we are here. 3, 4. Yeah, so in 4 checks. I was almost getting myself confused. So only in 4 checks instead of 5. And then we can even have one bigger level of detail where we just have the entire chunk either be 0 or 1. This one is 1. But of course you can imagine that there will be quite a couple of chunks which are just completely 0. Right? Completely 0. So yeah. And we don't even really have to worry about just getting rid of pixels that you can't even see anyway. Because this algorithm is going to take care of it all on its own. Like if there are like little voxels all around the side here, this algorithm will find these voxels rather quickly And then it will just instantly return. It doesn't have to check every single one in here anyway, so it really doesn't matter. So this should work. And of course, if we are only storing ones or zeros, we can store everything in bits. And that means that we can store 8 of these in 1 byte. That means that we are 8 times more efficient with our space, which is awesome. Right. So what I can do now is I can make a byte array. Can I make... Does it have something like a bit array? Yeah, it does actually have that. A compact array of bit values, which are represented as booleans, where true indicates that it is on and false that it is off. I'm not entirely sure about these bit arrays in C#. I don't know exactly how they work, so I'll keep it simple and I'll just use my own byte arrays. So this will be disk map 0. Then we need a disk map 1. So the 0 will be the full chunk. The 1 will be the first little area, so the 2 by 2 by 2. The next one will be the 4 by 4 by 4, or the 64 in total. This one will be the 8 by 8 by 8, right? So that will be 512. This will be 16 by 16 by 16, which will be 4,096. And then 5 will be the entire chunk. So these are just the same as voxels. So I'll keep this one out. So we only have 5 different granularities. I don't really know what to call it though. But yeah, sure. Like this. So this map 0 will just have a size of 1. Right? And that will just keep track of whether there are any voxels that are not 0 in this chunk. Then we have this map 1, which will have a new byte, which will also only have 1 byte in total, because 2 by 2 by 2 is 8 bytes, or 8 bits, right? So that fits exactly into 1 byte. That's nice. Oh, that was not the right one. The next one, this one has to store 64, so it's only 8 here. Every time I just have to multiply by 8, so this one is 64, and then I need the last one, which will be 512. So in total, we are only storing like under 600 bytes, right? So per chunk, it's under a kilobyte of extra data, while of course it is 32 kilobytes of actual voxel data. So this extra 0.5, a little bit over 0.5 kilobytes in disk maps is insignificant. We don't really have to worry about the impact on memory of this too much. Right, and it will have a huge effect on our performance. So actually this is great. Me trying to justify this to myself. Yes. Awesome. Also to you guys, of course. Okay. Now we just have to go over everything. So let me check. So I don't have to do any of these weird calculations anymore. I just have to set everything to 0, which it does automatically, so I don't have to initialize everything. Anything, I mean. So look at this. We went from all of this initialization code to literally nothing. This is already initialized. Everything is 0 because we start off with an empty chunk. Awesome. Now, if we do set something, if we do set a value, x, y, and z, then we have to do... It's not even going to be hard, is it? So, hold up. That's actually going to be extremely easy, isn't it? Okay. Let me explain. We just go here. We just get rid of any of this stuff. We probably want to check this somewhere, don't we? Yeah, we do. It's this one. You can go as well. Let's just restore this to its original state. Alt of that. Get rid of you. Awesome. Right, well. Of course, do this as well. Okay, so if value.color doesn't equal 0, so the value, the new color that we are setting is not 0, so we are going to set an actual color. And what we already had was 0. actually, I don't even want to check this. There's no need to check this. Because updating the disk maps will be so fast that checking this is kind of pointless. So actually, I'm just going to completely remove this. So if we are setting a non-zero value, then I want to go to disk map 0. Then I want to take 0. Index 0. And then I want to say, and... No, not even that. It's just going to equal 1. That's it. That's it. Okay. This at 1, 0. Now we are going to have to do something. Because right now I'm going to have to bit shift some stuff in. So remember, we will have 8 different values in here for 8 different octants. So we will have to get our actual X position within this chunk. We're going to have to divide it by 16, don't we? Because then we get a value between 0 and 2. 0 or 1. We divide it by 16. Dividing by 16 is the same as taking this out by 4, correct? Yes, that's correct. So X bit shift by 4, bit shift out by 4. It's the same as dividing by 16. Right, then we have plus 2 times y divided that by 4. And plus 4 times z divided that by 4. There we go, or shifted that by 4. So this will be an index. Right, this will give us the actual index in the 2x2x2 area. And then we can say we want 1 and then moved in by that index. That does not work because I cannot convert int to byte. Like b. Like what should I convert to byte? I guess I can just do this, right? There we go. So we bit shift in and int by all of this. And of course, this will either be 0 or 1, 0 or 1, or 0 or 1. Let's say all of them are 1, which is worst case scenario. This will be 1 plus 2 plus 4, which will be 7. So you can safely bit shift that in. Awesome. Now we are going to have to do some disk map 2. We're going to have to find yet another index. Okay. So first of all, using this index is awesome. We can just copy this here. But we will also have to use an index here. Should I use a 1 shifted in? Yeah. No. No, we actually have to use an index. So we don't want to shift something in. We actually want the index. So to get the index of this map 2, we probably want... Yeah, we probably want to divide by... not 16, but by 8. Right, so x, this all divided by 8. So this should be times 8 and times... That will be way too big, actually. Hold up. So we have this array. Right, so we have the map 2. M2, which is an array of 8 of these bytes. 4, 5, 6, 7, and 8. And then isn't 2 times x shifted in by 4 the same as... Oh, wait. Debug, you are completely correct. Do we favor speed over readability? I think the answer there is yes. Yeah, because now we divide it by 16 and multiply by 8, which is the same, or multiply by 2, which is the same as dividing by 8, of course. So yeah, absolutely this. And this should even be divided out by 2. And then this will be even faster than the previous one. That's amazing. Thank you, Deepak. Yeah, that's insane. Bit shifts, by the way, are basically the fastest operation you can do. It's even faster than multiplication. I believe it's even faster than addition. I'm actually pretty sure it's faster than addition. Bit shifts are insanely fast. Basically are 0. Well, they're not 0 cost, but they're like 1 cycle. And that's it. So it's insane. So we like this. and that is very much intentionally the reason why we are using powers of 2 everywhere, because then we can use bit shifts. Okay. So we have these, and all of them are 8 in value. So in total, this will be 64 bits, right? Now we want... now we can have 8 in here. Like 8 different 8 valued bits. So what I'm thinking, right, is... yeah, it's this situation, isn't it, basically? So what I want is I want this area to be in one of those bytes. This area to be in another one of those bytes. This one to be in another one of those bytes. And then that one to be in another one of those bytes. Right? So, I guess what we should do is to get this first separation is exactly the same as what we did in the M1 case, right? So we can basically say M2 and then X4 plus Y3 plus Z2. There we go. That can be our index. So it will just be one of these 4 in 2D, one of these 8 in 3D, of course. Then once we get that, then we need to separate between another 4 values. So I'm not entirely sure how we should do that. Right. Because I suppose this would be now a total of... we're at 64, so it's 8 by... no, it's 4 by 4 by 4. So we are 4 in width. Right, so we should divide 32 by 8. If we divide 32 by 8, then we get little 4 areas. Maybe we should do that first. It does seem a little bit excessive to do it that way. Right, if we divide x out by 8... yeah, so right now we divided that by 4, so that's of course a chunk thing. Yeah. If we do this one out by 5... no, by 3, then we divide it by 8. That will give us a value between 0 and 4. Right. I suppose that is what we will have to use here as well. Or that will give us a value between 0 and 4. And then we just mask it by 1, 1. Right? 0, 0, 0, 0, 0, 0, 1, 1. Or 3, basically. Right, so that will give us a value between 0 and 2 again. Then I can say the same thing about y. But then of course times 2, so this will now be shifted out by 2. And z will be shifted out by 1. And all of them have to be ended by 3. Will that work? Let's check that out. So let's say we come from this way. So first our value will be 0. Just x will be 0 in general. Then that will be 0. So we'll get index 0. And this will also be 0. So we'll get the first bit. I get to the next one. So that will be 1. Divided by 16, which will still be 0. And then this will be 1. Divided by 8, which will also still be 0. Yeah, I want it to be Oh, no, wait, because we increment here by 8. Yeah, so that will be 8. 8 divided by 16 is still 0. 8 divided by 8 will be exactly 1. And 3, so that is still exactly 1, so it's fine. Then we can go to the next one. That'll be 16. Right, 16 divided by 16 is 0. No, 1. Yeah, so we get the next byte. 16 divided by 8 is 2, but we end it by 3, which will still give us the value. 2 is 1, 1, right? No, 3 is 1, 1. 2 is 1, 0. So that will still give us what we want. Am I sure I want to end by 3? I think I actually want to end by 1. Because then it can be either 0 or 1. Think about that. So now it can be 2. So yeah, that's actually bad. Yeah, so it has to be end 1. Yeah. It has to be end 1 then. Because then the next one... Yeah, it has to be. Because then the next one will be 16. So the next one will be 24. Which will still be index 1 here. And then this again will be index 1. So you get 0, 1, 0, 1. Yeah, that works. So I shifted that by 3 and 1. Okay. And this one had to be the exact same, right? So... let's do that. This can be removed. There we go. This has to be a straight brace. There we go. Okay. And then here we can have our boilerplate 1 shifted in by that 3, 2, 1. And then of course... and 1. And operations are also placing fast, so that's totally fine. There we go. And we also need the 3 map. There we go. Which will have the index still here the exact same. So I guess I should just calculate this once and use it over and over again. But now this here should be end 3, I believe, for every single one. Because then you save the first 4 bits. So you get a little bit more granularity. Yeah, I'm pretty sure that's it. And then for 4 it's also trivial. Just increasing it by 1 more. So we have in like the same index again. Wait, but this will be between 0 and 8. Now here you need the index between... oh, you need this index. Yeah. Which will be between 0 and 64. Correct. Do I want to end 1 then? I don't think so. I don't think I actually want to end 1 here. The number man, because of the numbers. Yeah, well, you can notice that I am struggling a little bit with these numbers, aren't I? Numbers. Yes, this will be, let's say, 32 divided by 8, which will give me a value from 0 to 4. 4 plus this will be a value divided by 16. No, this will be divided by 4, so it will give us 8. 4 plus 8 plus 16. 24, 28. Am I doing this right? I don't think I'm doing this right. Yeah, here are my numbers, guys. My numbers are awesome. Don't you know? Let's see. So this will... What did I miss this last stream? No worries to cover it now. Or ever, up to you. So your name is Tommy. Is it? Why do you think that? Alright. Yeah, so Cases S. Welcome, welcome. Hey, so what are we doing? We are making some maps. We are basically going to say... Does it say in some places? I don't know where. Do tell me where. We're basically saying out of different levels of detail, are there voxels in our little subvolume or not? If so, then we have to look into it. Otherwise, we can just skip over it. Chrome? Chrome. Just like, if you open my channel in Google Chrome, or, you know, what do you mean? Mainly. Oh. Okay. Weird. Right. So we want to get a value between 0 and 64 now. So if we have x, we can basically say x divided by... What do you want now? X can be between 0 and 32. Of course, we want 8. Level detail in every single direction, right? So we just divide by 4 plus 2 times y divided by 4 plus 4 times z divided by 4. Was that the idea, basically? It made a sign in with a no-numberman deluxe account and some other account. Made a sign in on your stream. My stream? I'm thoroughly confused. My brain is already being fried by these dang bit shifts. Hard to explain, yeah. It's okay. Yeah, so this channel did used to have a different name in the past, I suppose. It's kind of stuck then, I guess. Weird. Right, yeah. So we have x divided by 4. But then we need plus 8, right? Y divided by 4 plus 64. Z divided by 4. That will of course be too big. 4 times 8 is that though. You opened Chrome while streaming and in the corner it said sign in and it suggests 2 accounts. Oh, did it? Oh, yeah. That is how you got that. Now I understand. Yeah, so I do have another YouTube account. And that is basically my old YouTube account that I made years ago. You know, over 10 years ago. Back when I was just a wee little lad. And I just used that to actually watch content. And I don't actually watch that many videos on the No Numberman account. The file system says it too. Oh, yeah, because, you know, I made my Microsoft account, I guess, when I basically also made a YouTube account, so I used the same usernames and stuff. Yeah. Very nice. Yeah. Very true. Good stuff. Not my actual name, though. I'll leave you all in great suspense on what that is. Between 0, so 64 was the oh yeah, we want the 4 by 4 by 4 situation now, so we need to divide by 8. Yeah, I see what our issue was. Okay then, your name might be Fred. It might be. Might be. Maybe my name really is No Numberman. That'd be awesome. 16 z divided by 8. Yeah, so, right, this is x shifted in by 3, or shifted out by 3, I mean. This is y shifted out by 3, shifted back in by 2. And this is z shifted out by 3 and shifted back in by 4. So in total, this is going to be x right shift 3 plus y right shift 1 plus z left shift 1, which is kind of interesting. But yeah, this is what we're going to get then. 3, 1, and then the other way 1. And this, the readability of this is just awful. It's just garbage. So I guess that's a disadvantage of trying to be optimal here. I'll be only listening till this makes sense. Yeah, good idea. We'll be done with these dist maps probably pretty soon. Hopefully, if my brain can manage this, then we can get to the actual ray marching again, which is way more interesting. Right. Then. Let us see the actual values here. Like every single thing here, right? Every single little cell only has a 2x2 little area, doesn't it? Yeah, it does. Totally does. So we just end by 1 still. But I probably want to do the same thing here, right? Four, 3, 2, and this is then 3, 2, 1. Is that true? Why not use 4, 3, 2 here? That was because does this then make any sense? Oh yeah, you just divide everything out by 1 more. Right. Yeah, so I need to add 1 more shift to everything then. Does that make sense? Shouldn't I use like this shift for this one? I'm thinking so. I'm thinking this should be by 1 and this one, this direction by 1. Agree, Visual Studio 2022. Oh, wait. Yeah, I agree. Visual Studio 2022 is epic. Is it? That'll be still a while before that releases now. Is there even a Visual Studio 2022 announced? Like, I'm not even nearly in the loop on that thing. Right, this will give us a value. Yeah, no, this should be okay. It should be okay. I say Visual Studio 2022 preview has some issues, but it is nice. Oh, good. I always like new stuff. Now, this should be correct. And then for this one, because now we of course have our 0 to 64, but now we need our 0 to 512 situation, which will be 8 divided by 4 plus 8 times y divided by 4 plus 64 times z divided by 4, which is still x3. Will then be plus y shifted in by 1 plus z shifted in by 3. It's divided by 4 is 16. Multiplied by 16, isn't that shifted in by 4? That's insane. And then the last one, no, not the last one, but 0 to 4096 will be x divided by 4 again. No, x divided by 2, so this should also be bit shifted by 2. X divided by 2 plus, and then we have 16 times y divided by 2 plus... What should we have here? Times 16 again, which is 512, right? Times z divided by 2. So this is just x shifted once, plus y shifted the other way 3 times, plus z shifted the other way 7 times, like 218. And then the last one from 0 to 30 to something something. That is just x plus y plus z normally. Right? Because these will all go to... Basically what we get is x divided by 1 plus... Oh wait, don't we get an issue here? Then we get 32y divided by 1, which is of course... Oh yeah, but that also, this will of course be index. So this is just plus 32 times y plus 500. Like 32 times 32, yes, 4096. Is it? What's 32 times 32? It's only 1024. Times... See. What is 16 times 16 then? Is that not 512? No, it's 256. Aha. My bad. 8 by 8 is definitely 64 though. Right, and then with 256 divided by 2 is only 128. Yeah, which is... So, yeah, so that's correct. That's correct. So this will be the index. Right, right, right. Yeah, so this will be either 0, 1, 0, 1, 0, 1. That will shift things in. Will it be correct though? 0, 0, 0, but that will also have the same shift as 0. Like 1, 0, 0 will have the same shift as 0, 1, 1 now. It's a bit of a thing now. Oh, we're still not quite there, but at least this idea is there. So for the for map, we do this by 2. 0 to 250, yeah, 512. 2, left shift by 1, or right shift by 1. And right shift by 4. Now we will get all of those values. Oh yeah, now this one will be... Yeah, this one will be 0 or 1. This one will be... like 2 or 3, and this one will be 4 or 5, something like that. This one should work. We will bit shift in by either 1, 2, 3, 4, 5, 6, or 7. But these should also give us values between 0 and 7. So this should actually do plus 2 times this, plus 4 times this, which means that we also have to bit shift out by 3 here. Bit shift out by 3 here. No, and then we just have to add the other bit shifts in later. Divided by 8, which is 1 more granularity, yeah. Divided by 2, divided by 1, yeah. This is 2, 2, 2, 1, 1, 1. So we have to shift out, and then we have to shift back in, actually. Because this is, of course, times 2, which is the same as shifting this whole thing back in by 1. Shifting this whole thing back in by 2. Yes, I do believe that this should be right. Oh, and here and 1, of course. There. Yes, and this should all have the same shifts because we want everything to be between 0 and 8. So that should actually be completely fine. Yeah, so here we could do that together. Like take them multiplying by 2 and shifting out together. So then we just shift to the right by less. But here we have to do it in different steps. So we can't take it all out together, but of course this is quite nice. So basically here we divide by 6. No, we divide by 2. Then we just take the first bit of that. Right? Yeah, and then we shift back in by 2. Yeah, that will give us the right index. Sure, sure, sure. Do we need anything? Do we need to store anything, basically? I don't think that I will. Maybe the compiler will store a couple of things for us. I think this will be okay. Right, and then in the other direction, we will of course have basically the same thing. So if we actually store a color to 0, then we have to find the index of this color of our X, Y, and Z, and we have to set it to be not 0. But that is basically the exact same thing that we just had. We just have to set things to 0. So here we have to shift in 1. Oh, but here we of course... Right. So we have to OR it, like OR equals here. So basically, I mean here, right? And here everywhere. Because basically we don't want this to change any of the existing bits. We just want to be able to set something that's not set yet. So basically if we have 8 bits that look like this, 0, 1, 0, 0, 1, this is 5, 6, 7, 8. And we want to add a 1 there. Then we can just say equals 0, 1, 2, 3, 4, 5, then the 0, and then 2 zeros. If you do this, then of course all of these bits just get removed out. If you do the OR equals, then that will be correct, right? Because 0 or 0 is still 0, 1 or 0 is 1, 0, 0, 1. Then we get a 1 here, 1, 1. So that should be correct. If we want to set a particular bit to 0 though, then we should say, if we have our original situation here and we want to set this bit to 0, then we have to do AND equals and then the 1. I guess we could say like the opposite, like the inverse of our 0, 0, 0, 0, 1, 0, 0, 0. Right, so we can still set the same bit, but then we just inverse it. So that everything here turns into 1 except that one that's 0, 1, 1, 1. If we AND that, 0 and 1 is 0, 1 and 1 is 1. So we get all we want, right? Right. So for this one we have the OR. Here we can just set 0, of course. Here we have to do AND. And the opposite of that. It doesn't work because system index. What is the not operator? Is it that? I have to look that up actually. C# not operator. The bit not operator. Doesn't even exist. Bits operations. Just shifts though. Oh no. Point by bool, yeah. So the bitwise complement, yeah, that is what we want, I think. So what do we have here? Bitwise complement, right? That brings the bitwise complement of the, yeah. So if we have 0, 0, 0, then we get 1, 1. Yes, that's correct. This is the left shift, then we have the right shift. What was the other head thing then? Computes the bitwise logical exclusive OR. Okay, that's it. We just want the OR operator for this, of course, not the exclusive OR. And here you want the NOT operator. This can all be AND. This can all be NOTted. There we go. So actually extremely easy. Setting it one way or the other way, very easy. We don't need any of these functions anymore. We don't need to get distance. This brick empty. Ink, this map, this bit, like that, this random stuff. We don't need any of it. It's a way easier to update. We just set all these maps. Just change them. We just do some bit operators and we change them. So it's so fast. It's so fast. Awesome. Okay. It is a mess though. It's only a little bit confusing, but only a little bit. Only that it took us like nearly an hour to make this. So I mean, you can hardly call this hardly call this confusing. Got a little sip. Oh man, thirsty work. You wouldn't expect it, but it's true. Right, and then I also need an int level here, because basically I want to change this to the just our function, our bool function. Has content or is empty. Let's just do it is empty. And then we want a level here. So level 0 should just look at our basic voxel, see if it's empty. So I suppose this actually should be 1, this should be 2. Right, it should be level 3, 4, 5. Same thing here. 1, 2, 3, 4, 5. I could make another bitmap for just the voxel thing. So I have another distmap 0, where we have 1 bit for every voxel, but I just don't think that's necessary. Might as well just read out the color right away, right? This can go actually. It's nice and compact now, compared to what it was before, that is. Okay, so it is empty, and then here we want the level. So first of all, we want to check if level equals 0. And the thing is, right, probably, maybe we could have made this just an epic template function in C++, but that ain't gonna work, so we have to actually use these ifs here. So if it's 0, then just return, and then we should just get voxels, the x plus, you know, all of that sort of stuff. Let's see, can I get this chunk length? Times y plus chunk length times chunk length times z. Of course, maybe what I should actually make is a public const int chunk length shift, which is just 5. So then we can just do y shifted in by chunk length shift, and then z shifted in the other way, shifted in by these two adds. Alright, because times 32 is just times 2 to the power 10, which is the same thing as doing this. And then this dot color, not alpha even, but dot color doesn't equal 0. So if it's empty, oh, then it don't equal 0, sorry. What is the problem with this? Actual shift count equals 0. Left operand will remain unchanged. Oh. Thank you for telling me. There we go. There we go. Okay, otherwise, you have to get one of these maps. I suppose we should actually just get a switch statement in here now that I think about it. Maybe we should just make 5 different versions of these for all the different levels, but for now, I suppose we can just do like a return level switch And then here we can get 0, which should return this thing. And then defaults should return false. So if we get anything that is weird, just check it, whatever, I guess. It's annoying, but sure. If the level is 1 though, we should check this map. 0. And then of course we have to shift it out. Like we have to do and then a certain value, right? Here and then double equals 1. Double equals 0, I mean. Okay. Like this should work, right? Now we just have to find a proper AND value here. Okay, let's see. So what do we have? Here we have, it is basically this thing. And the byte of it. Is A plus faster than A shifted in by 1? Do you just mean like a... Oh yeah. So a bit shift, I do believe bit shift is faster than addition, yeah. Maybe that is not true for C#. C# bit shift speed. Can look that up, of course. This is another thing. Blah, blah, blah. Okay, the benchmark. You can, of course, always do this. The AND operator takes longer because it is the first loop. If I switch the AND and OR, yeah, so it all takes the same, so it's all very fast, but bit shift versus addition. I do want to check this, by the way, because I'm not 100% sure myself. On older microprocessors. To clarify. Asking about the circuit behavior, not the number of clock cycles. In any binary bitwise operation, each output bit depends on only the 2 corresponding bits in the inputs. In an add operation, each output bit depends on the corresponding bits in input and all the bits to the right. Oh yeah, of course. That's how we learned to do addition back in the day. Elementary school. It's actually true. In its simplest form, an adder adds the 2 low bits and produces 1 output bit and a carry. Then the next 2 lower bits are added and the carry is added in, producing another output bit and another carry. This repeats. So the highest output bit at the end of the chain of its adds, if you do the operation bit by bit, as older processors did, then it takes time to get to the end. There are ways to speed this up, some by feeding several input bits. Okay. So today's processors have many different units for performing various sorts of work. Blah, given today's capabilities, the work of doing an add is small compared to other tasks, so it fits within a single processor cycle. Okay, so apparently nowadays it doesn't matter. But yeah, I guess my knowledge was based on older processors for some reason. I don't know why. So yeah, interesting. So if we get this, right? We just take this thing. This will give us a value between 0 and 7. No. You could write... So you could write chunk length shift by 1 instead of chunk length shift plus chunk length shift. No. So shifting 1 to the right is this, or shifting 1 to the left, sorry, is the same as multiplying by 2. So it's not... Oh, wait, yeah, no. I'm stupid. Yeah, that's absolutely correct. Yeah, no, I'm stupid. That is entirely correct. Yeah. Yeah. But, I mean, if it doesn't matter, right? If on modern processors it doesn't matter, you should probably do the thing that is more readable, which is the second case, just adding the 2 together. It's the one thing that I don't particularly like about this code. It is the readability is just horrible. It's horrible, right? Okay, so this should still be shifted. Should shift 1 still. So this will read 1 bit. Okay, so that's perfect. Maybe I should store like this thing somewhere. Okay. Now let's see if we have 2 here. Then we need to read from this map 2. We need to, of course, still have a 0. Oh wait, I kind of did this backwards, didn't I? Shouldn't this be 5 and this be 1? Or this should be 0 and this should be 5. Maybe that makes more sense. 2, 3, 4, 5. So we do the same thing here. 0, 1, 2, 3. Because this one is 32,000, then this one is 1, this one is 8, this one is 64, you know, so it's a little bit out of line. 0, 1, 2, 3, 4. So that's nicer, better form. 1, 2, 3, 4. What's going on right now? We are trying to, well, find out if one of these disk maps, with a certain position in it, is empty or not. So we are basically just reading out these bits that we just put in. Right, so level 0 actually is not the voxels. Voxels should go all the way down here. This is 0, this is 1, and this is 5. Okay, so this is 0, this is 1, this is like this is just and 1 double equals 0. There we go. That is still correct. Then if we go to 2, then we need to get this map 2, then we need to get this nice little thing. Index, and then we need to get this index. It is nice that we can now just kind of read this out. We can just copy everything that we have. This doesn't work, presumably because we are missing some parentheses. Yeah, we do. Or we are. There we go. It's a little bit verbose. Yeah, like using macros for something like this might be useful. Can we even do something like hashtag define and a second number? No, we can do that in C# function. Unfortunately, you can define just names, but you can't define sets of characters that you then just insert everywhere. It's just so nice about C++. It's so nice. I love it. Then we have number 3, which has this index. There we go. Do you guys know of a way that I could store like these bit shifts somewhere? Like somewhere constant? Possibly using and then some name. I don't think so. Maybe at the top of the file actually. Using some name equals. Okay, that's always my preferred thing, I guess. We could name it shift equals. Yeah, that doesn't really work. It has to be an identifier. Not sure what, maybe just 4. No, that doesn't work. That's a shame. Worth a try. Worth the try. Okay, and then for number 3 we need this thing. Yeah. Wait, that's the same thing? No, it isn't. Okay, good. Using project equals mc.mycompany.projects. Yeah, I mean, yeah. This is from the Microsoft website. Yeah, no, but yeah, that is true. But I mean, I want to do something like Right, if I have like const shift equals 5, const int shift equals 5, I want to have something like this defined, but even better would be this. And I just, everywhere where I type something, I want this to be put in its place, basically. So it's like a macro in C++, but I don't think that that actually exists in C#. Okay, then we need this one, so that is by 2, bit shifting this one by 1, and this one by 4. A function. Yeah, but see, a function would add overhead. Right, because you have to call a function and it has to take, like, evaluate it, all of that stuff. Function pointers, you have to go to a different point of memory, you have to evaluate it, have to go back. It has a bunch of overhead. But in C++, what you can do is you can have a macro, is what it's called, and it's basically just like a name, and then just some, like a line of code after it. And everywhere where you insert that name, the compiler will just replace that name by whatever text you put behind it. So you can just paste entire functions just in the middle of your code, and you can just paste in like x shifted in by 4, even though x is not defined outside the scope, of course. But if you place that macro inside of a function where x is defined, then that is not a problem at all. It will just put it there, and as long as it can compile, it will just do it. So it's awesome. It's absolutely awesome. These are all bit shifted to the right by 1. Correct. Then we have 5, which will take this one, and then we have this false. Yeah. I think this is it, though. I think this is it. Hashtag define. Yeah, exactly. So I already tried that, right? Because that is indeed how you do it. Yes, it's a pre-processed thing, exactly. So in C++, what you would do is you would define, and then let's say macro, and then behind here you would just type something like x multiplied by 4. But here it doesn't work because C# is not built for macros. I'm pretty sure. C# macros. No, C# does not support preprocessor macros like C. Visual Studio, on the other hand, has snippets. Are a feature of the IDE and are expanded in the editor rather than replaced in the code on compilation. Hold up. Oh, okay. Right. How to use snippets, code snippets. Yeah, I don't think this is quite the same thing. Yeah. Sad. Nah, it's a good thing that we're looking this up, because it would be awesome if we could find something like that, right? But it doesn't look like it. Oh well. Snippets are like you writing if and then press tab, and then you have if complete written for you. Oh, like that. Oh, yeah, like that. That's just useless. No, I'm sorry, it's not useless. It's not useless. But it is very, very different from what we're trying to do. It's useless for our situation here. But okay, we are 1 hour in. Let's evaluate. We updated our disk maps instead of having actual disk maps, which I guess I shouldn't call them disk maps anymore. Maybe that's a good idea. Maybe I should actually change. Yeah, the thing like CTOR, exactly. Yeah, I think you said something about CTOR last week. Yeah, it's kind of nice, but yeah, it's not a macro. Anyway, we made these disk maps. So now we actually have these bit maps, which are literal bit maps, not byte maps, where every bit is just 0 or 1, of course, and it represents whether a certain sub volume is empty or if it is filled. I'm not quite sure on the naming of this. Let me know if you have a good name for something like this. So I don't think that I do. Super voxel, that sounds bad. And it still is a map, of course. This basically comes down to a flattened octree, right? That's why I basically call it this way. Because in an octree, you would enter here, and then the octree would tell you where the next quote-unquote super voxel or subvolume is, and it will just automatically give you that subvolume. In our case, we have everything predefined in just a flat array, which will always take up the same amount of memory, so you don't get any of the memory saving capacity of an octree. But everything will be well behaved. Let's just say it will always take up the exact same amount of memory, which is actually incredibly nice when working with a graphics card. And all of the data will just always be there. You don't constantly have to update the thing, which again is very nice when working with a graphics card. So I think this is fine because it doesn't add that much memory anyway, so it's fine. Maybe we want to do some sort of optimization for the actual voxels, because of course the actual voxel array has to store the actual colors, meaning that, you know, it takes up 8 times as much memory, aside from already taking up 8 times as much memory because it is just one layer lower. And so it takes up 64 times as much memory as this one. It's our highest definition map, which means that actually this one is significant. Voxel array is significant, the rest is fine. Okay, anyway. I think it is time that we actually go to our render manager. Let's close some of this stuff. And then we can just get started with actually making the new ray marcher that I had found on the internet in a nice paper. Right, let's get started. So we now have our bitmap, quote-unquote bitmap, with all of our colors. We go through all of our pixels. For every pixel we make a ray with a certain origin, with a certain offset. Finally, yes! You have a certain direction for every ray, yeah, which is also different from every ray, which is awesome. Then we have, of course, the current position is the origin. Then the current chunk position is just the origin divided by 32 in every direction. Then we have our output color, while not output color. We don't actually have to get the chunk, although I suppose we should get the current chunk. Can we just do world dot sort of get chunk? We should get like you know what, it's fine. It's fine. We can probably do something in world to make this a little bit easier to get our maps from the world directly instead of having to get the chunk first, but fine. You can use normalize faster to be faster, lol. Where do we normalize? In here. Ooh. I don't even think this needs to be normalized. The direction plus, oh no, it definitely does need to be normalized. Normalize fast. Oh, I like that. I like that. Oh, doesn't give anything back. Oh, okay, so I have to do this, and then we have to do dir.normalize fast. Right, it does it in place. Yeah, okay, there we go. Nice, thank you. What about OpenGL? So we will be switching to OpenGL whenever we have it working on the CPU. So the thing about working with a graphics card is that it is an absolute pain to debug. And so in order to prevent some of that pain, I decided that I wanted to build the ray marcher first on the CPU, and then I want to basically quote-unquote copy it as far as that is even possible, but you know, conceptually copy it to the graphics card in hopes of already picking out some of the bugs here on the CPU side, where it is still very easy to set breakpoints and find the issues. So that's the plan. Let us see, because then we first got the chunk. If chunk is null, then we just return that as all fine. That is all fine. Then here I want to set the level as well. We do here while true. I think I kind of just want to get rid of all of this, because this is going to be somewhat irrelevant now that we have a completely different way of traversing the voxels. Right. So here we go through the voxels. So what do we need to do? So first of all, we need to go through and then lowest level of detail. Level of detail. So i.e. level equals 0. Then, if not empty, go one level lower. Then we need to repeat that. And then if it is empty, no wait, if a color is found, then return color and end. So you will be doing LOD as well. Not gonna lie, LOD sounds mighty familiar. But currently, I don't quite remember what it stands for. Oh, I feel like that is so bad. It's so familiar. Level of detail. Yeah. Oh, I want yep. Well, let's just pretend that that never happened. So, if found the color, then we return the color. Yeah, but yeah, we will be doing level of detail as well. Completely true. So, right, what we can do here, or maybe people who might not be quite as familiar with these voxel renderers, what we can do here is, if we have this like level of detail, if we are far enough away from the camera, we can say, well, if there is a voxel in here, like in this area, then you know what, who cares? Let's just return the average color of this whole area. And I'm not even gonna care about whether or not, or where exactly the voxel is. We just have some sort of average color in here, which might be like OX, C2, whatever. And we just return that, and that will be the color of the thing. Done. Then we don't have to traverse quite as deep. We don't get as many array like near misses, where there is like a little voxel there, and our array goes like this. It's just like, now our array has to go even further, more calculations, pain, all of that sort of stuff. So yeah, the level of detail stuff is amazing. We'll be doing that at some point. If color found, return color ends. No color found. Oh, yes, there we go. My stream chat just kind of died, but I just refreshed and it seems to be up again. Okay, awesome. If no color found, then proceed in current level of detail. Yeah. Then 6. If end of our current level of detail, LOD move up one level. And then repeat. 7. Repeat. Basically, right? Basically it. Okay, maybe actually 7 is if end of chunk. Then get next chunk. 8. Repeat. There we go. We might also want some sort of rate terminator, where if we have gone, let's say, 1,000 units in distance, we just want to terminate array. But at some point we just run into a null chunk anyway, and that will automatically terminate. So it's fine. We probably want to do something with rate termination at some point, of course. Keep it simple for now. So go through lowest level of detail. Sure. So I suppose we should just do something like while through. And then in here we should have int level equals 0. And while through. What we then want to do, so we want to get our current position, right. So our current position, and we want to get our current level of detail. So if now I need to get our current chunk, we know that it is not null, is empty, and our current x, y, z. Do I actually have an x, y, z here? It can just be position.x, position.y, position.z. Position.y, position.z. Level. If it is not empty, only then I want to do something. I guess if it is empty, then I just want to move on. Right, then I want to move on. A plus 1, something like that. Else does not work. Should work. Pos.x. Yeah, so we probably want to do something with this. Get our like, integer position, right? Something like that. Oh, we want to get our sub chunk position. Right. So we can get out of here. We can get vector 3i, and this will be our I-pos integer position within the chunk, which will be very similar to this. We need to floor it first, but then we need to end it with 32, which of course is 0, 0, 0, 0, 1, 0, 0, 0, something like that, right? Was it again like 31, right? That is just 1, 1, 1, 1, 1, 1, all the way up. And 31. And 31. That will be our integer position, and then for that we can get our x and z. That should always be in the chunk that we are. Yes, unless we are negative. Huh. What happens if we are negative? Like negative 5. Can't we just say that is this and then minus chunkpos dot x and then shift it back up by 5? So this will be like minus 4 minus 32, which will then be positive. So that should actually be better, right? That won't give us any negative values. And that won't accidentally absolute value something that we don't want the absolute value of. So I think that this is correct. There we go. And Z. Okay, awesome. X, Y, Z, and then our level. If it is empty, then we need to move on. So that means that we need our intersection algorithm. Let's see, how do they build that here? So they do have some sort of t distance. Actually, they built this inside of the function that they're working with. So like z and step z, they directly update that. Let's see whatever we need. Yeah, so we'll just start off with a public pool and then another intersect. So we don't have enough of those already, but sure. Then we will just return false for the moment. At least it shuts up about the error. Right, let's see. This of course just continues and continues, but we don't really want that. We just want to find one intersection. Let's just copy paste this. Don't really care about the rest. It's actually not too bad. Kind of formatted somewhat the way that we want it to. Okay. So we need a float t max x, t max y, and t max z. We also need an int x, y, z, step x, step y, step z. Now, everything is not initialized, of course. So only initialize z? Yeah, sure. Okay, so tmax x, this is all just going to be 0, right? At very first. Wait. We do kind of have to like calculate tmax x, perhaps. Let's see, how do they do that again here? Next, we determine the value of t at which the ray crosses the first vertical boundary. Right, but they never actually show how they do that. Oh, that is very interesting. Okay, well, I suppose we have to kind of do that ourselves. Okay, so int level. Good evening. Now, yeah, we just need the level. Maybe we need like the beginning actual position. Right, we probably like a vector 3 position and level. Right, so from level we should be able to determine what our max x, y, and z will be. Position should therefore be our relative, like, local position and not our world position. Right. Okay, let's look at this in Paint real quick, get at least some idea of what we're doing. So let's say we have something like this, right? Level is just, I don't know. Let's say this is just 1 in size. Then we have our position, which is this, which will be like 0.4, 0.4. Yes, Paint, the best project planner. It is, absolutely. It is too convenient to pass up. So let's say that this is our direction. Right, then we can find some sort of t, for which we find that our starting position, which we will call u, right, in the paper, plus t times v, which is v is our direction, and then the x components of these will be greater or equal to 1. Right. Well, at that point, we can say something like... Yeah, how do we actually get t then? Then we have to do t times vx, which is not a vector anymore. Why am I doing this in like a 30-degree angle? That's ridiculous. So t times vx must be greater or equal to 1 minus ux. So then t, well, I guess when they are exactly equal, right? T is exactly equal at 1 minus ux divided by vx. Okay, that makes sense. That is, of course, in the positive direction. Once we are moving in a negative direction, that is another thing entirely. This makes sense. Right? So they do something with that, actually. It's like the step x. Right, so I need my vector 3 and then direction. I can say int and then step x equals, and then here dot x and then the sign of this. So math dot sign of this thing. This will then be an integer. Doesn't work because there's a step x there. There we go, and this isn't even necessary. Okay, awesome. Same thing for y and z. We will need these. Of course, these, the steps, are constant. At least for one ray, they are constant. So I could, of course, predefine these pass these to the function, probably very useful. We'll do that in the future. Then we could say that t max x equals, and then step x greater than 0. Then we have to do something else, right? So if step x equals greater than 0, then it will be this thing, right? So it will be 1.0 f minus, and then it was minus the u. Yeah, minus pos.x divided by dir.x. And yes, we can 3 divide dir and then get a 1 over dir, and well, maybe we should actually kind of do that. So vector 3, and then dir, and then inverse equals, and we inverse like this, vector 3 dot inverse. Doesn't actually exist on OpenGL, a bit of a shame. 0.0f divided by dir doesn't work, I believe. Nope. So I'll have to just make a new vector 3. It's a bit of a shame. Why does OpenGL not actually have an inverse function in their vectors? Oh, keep mistyping as well. There we go. And then we can just multiply by the inverse times x. Be a little bit more efficient. Otherwise, we want to do the same thing, but then in a different direction. So we want to do this when it's equal to 0. So then we have something like t times vx is equal to minus ux. So then we get t equals minus ux divided by vx. Yeah, and then of course, because u is always just positive and v will then be negative, vx will then be negative, so these negative signs cancel out and you get a positive value. So that sounds reasonable. Otherwise it is minus, and then u, which is positive x, times the dir in x. Right. Now do the same thing for max, y, and z. Actually easier than I expected. Expected this to be a bit more work, but maybe I shouldn't say that too hard, too loud. And then the z, step z, plus c, dir z, plus c, dir z. There we go. Okay, awesome. Then we should say int x, y, and z is not really relevant. We could, of course, have... No, that's actually completely not relevant. We should have some sort of output. An out for 3i, and then like change, like d, p for like d position, whatever. And then, yeah, we can set that at a later point in time. Okay, so if tmax smaller than ty, and if tmax x smaller than tx, then we can say our current x equals x plus step x. So we can just say dp equals unit x, right? Actually, no, I can just set it to step x times unit x, which is either 1 or minus 1, so that's actually completely fine. And then we say, yeah, this is our out of bounds check, which we don't need. And we always return true here, actually. So maybe we should just return a vector 3i, because intersect will always return true. And tmax equals tmax plus delta x. Oh yeah, so then we can still make our delta x out float delta. And then we can find out with our vector 3i output in what direction this should be, x, y, or z. Right, for now, tmax. Oh, this is just a t delta actually, it doesn't really matter that much. Okay, so tmax. Oh yeah, this will just update tmax. Here we have to recalculate it every single time. That's a bit of a shame. Yes. That is a bit of a shame. But that will kind of be necessary. Yeah, we'll just have to recalculate this for every step. That's okay. That's okay. Our level doesn't really matter, does it? Because here we said, oh, this is 1. Oh, I guess this should be 2 or 3 or whatever. So our size. So this shouldn't be level, but size. And then this should be size here. There we go. So then we can return this thing, which apparently, oh, because we haven't set delta yet. Yeah, that's fine. What will delta be? That is just Tmax x then, right? Maybe plus a little bit. Because at this point, this will just be exactly the distance. And maybe you want just slightly more. Doesn't matter. Yes, I think so. I think we should add epsilon, just in case. Plus float. Right, just a tiny extra nudge. And that is just to prevent that if we... Wait, let me zoom out because we are out of space already. Oh, I just wrote incredibly inefficiently. That is also very much possible. Right, so let's go here. Let's say that we have 2 of these boxes right next to each other. Oh, those are awesome. Awesomely drawn. Thank you. Thank you for the compliment. Anyway, so here, let's say we go this way. And now we find this intersection right here. Let's draw it like here. Let's say we find this intersection right here. Now in the next voxel, we're going to draw... Oh, wait. Yeah, so in this next voxel, we're going to, of course, continue our array. But I was thinking that maybe we will intersect here this line first before it will intersect this line, because maybe some floating point errors. This point will be offset to the back just a little bit. And then once we draw our line, we will hit our left wall first. But actually that's not true because we are specifically checking for if our x will exceed 1 or will be equal to 1 and not equal to 0, which it will be there. So actually, we don't need this. Delta equals t max x, and we do that. Awesome. Else, we say delta equals the t max z, and we return the thing here for z. Step z, unit z. Yeah, can we do something more efficiently? I guess it doesn't matter because you will always have to do 2 checks. Can't we do like an integer or something and then only have to check 1 integer? I do prefer that. Like int. Yeah, but then we actually have to do more checks, right? Because then we can have an integer that is unique for every single outcome. But then we have to check every outcome first, and then we have to check W again later in like a switch statement. So we have to do double work. So actually this is very bulky, but I guess it is the fastest way you can do it. It's insane. T max y in any case, and y, and here we have the z situation again, which, there we go. Yeah, you know what? Extremely nice. This is a duplicate function. Oh, static, of course. There we go. Need a position, a direction, deconstruction, use deconstruction. No, I'm not going to use that. A size and a delta. Yeah. Okay, fine. We can say intersect. Here. So it is empty, so we can just intersect. Load d equals, or I guess we should just call it t, no? Oh. Because in the algorithm it is called t everywhere, so we might as well just call it t. So here, this is just our position. That should be our relative position. So this is the integer relative position, and then we should also have the like actual relative position. That'll be this one, and then actual relative position in our floating point thing can just be origin.x, and then of course we subtract 32 from that. Yeah, origin.y. Wait, that shouldn't even be origin, that should just be our current position. Oh. Yeah, our current world position. Yeah. That one, and then that one. No more floors. Minus this, yeah. Okay, perfect. This should be our relative position. We can use our relative position, we can use our direction, we can use our size, which in this case, of course, is level 0 is size 1. Yeah, so it is just 1 shift to the left by level, no? It just happens to work out that way. And then... oh, you have 2 different versions here. Outfloat t. Oh yeah, so this will be outfloat t, and this will be vector 3i. And that will be our dp. Something like that. This isn't quite correct, I suppose. Invalid embedded statement. What do you mean? Never actually heard that. Like, why is that? Is this invalid? What do you mean invalid? Fix formatting. Sure. Oh, this thing is the issue. Yeah. There we go. Okay. Fixed it. Fixed it. But of course, size should actually be the biggest now on level 0. So actually, it is 1 shifted out by 5 minus level. When level is 0, it should be shifted in by 5, making this 32. Right? Perfect. If we go down 1 level, we get to 16, yeah, and then 8, and then 4, 2, 1. Yeah. Perfect. Okay, then we can say our integer relative position plus equals dp. And then we can say our relative position can plus equals our t times direction. And then our actual position can plus equals t times direction as well. Maybe the relative position should just be updated every time? I don't know. Yeah, because the relative position is now basically the same as the world position. But not quite, but similar. Anyway. Yeah, now is it? Like, it's basically like the same thing right now. It just has to be recalculated now. Because we are getting a new relative position right now. Yeah, so we just have to take this one out. Put it there. Integer position as well, by the way. Yeah. So, of course, we have our chunk position. Integer position. What do we even need that for? Yeah, that's for like the internal thing, right? Yeah. Maybe we do leave the internal position here. Yeah, the relative position is definitely just the position. And then moved in by 5 minus level. There we go. chunk bus.x. Wait, no. A relative position. Wait, hold up. So our chunk position is between 0 and 32. Can we move that in by 5? That doesn't make any sense. So we are only making this bigger. Oh, yeah, so you can divide it by 32. Chunk positions, of course, 0, 1, 2, whatever. Yeah. And if we are a higher level, should be quiet right now. Yeah, I mean, it happens. We're just breaking our brains over this one again. So that will give us a value between 0 and 32. Right, if we just do that. But we can also go higher. Yeah, so if you do minus level, if we go one level up, then we will go to 16, so we'll... Yeah, like shift in by 4. So if we have a position of 1, then that will be 16. If we have a position of 2, that will be 32. So it has to be plus then, maybe? F in chat for T-min value, but with this really long and unnecessary name. Is it? Wait, do I have some dumb name somewhere? No, I would never use dumb names. I'd never. Absolutely never. Okay, my data representation is just bad. Right. Our current chunk position. Just everything. So that is fine, but I don't really want to use chunk position over here, right? I can get like the relative position from this, and that is fine. This is our relative in chunk position. Right, that's fine. And our actual relative position should be different. I guess we can just set it here, and that is completely fine, right? We can set it here. Like this, it's completely fine. Then we have to do something clever with it later on. Right? Right. F in chat. Cause T-min value, but with this really long and unnecessary name, got a convenient name instead of the stuff I name my variables. Yeah. Well, to be fair, I had this professor once, right? I actually had him like 3 or 4 times. He gave a lot of courses in computer graphics, actually, which is, of course, the thing I basically enjoy most about computing science, so that's why I'm doing this. So that professor basically just did something like A in B is like 1, int in D is 3, then we have a float, and we call that A3. A2. That is just A, but then times 2, something like that, you know? And it was so frustrating to read his code, because basically his computations would just be like A, P is just A plus 7 times B divided by D times A2 times A2. Bit shifted in by A, of course. Almost forgot. And you get stuff like this, and it's like, okay, what the heck does this even mean? So actually, I really do kind of prefer prefer big, verbose names at this point. Believe it or not, they can be a bit ugly, but they're hella useful. Anyway, what do we want to do here? So we say intersect, but we are at a certain je ne sais quoi, right? So at our level 0 here, our real relative position, vector 3, real relative position, that is just a chunk position. That is just a chunk position. Right, and we just copy that over, actually. Right. So then we just do... Oh, integer relative position, that's what I mean. Right. So we just say, okay, this is our... oh, this is relative to our chunk position. Yeah, okay, never mind. Relative to our chunk position. So it's that, yeah. Then we want the dp, and dp will basically be... yeah, I guess I have to vector 3i, and then... yeah, integer relative position, and times dp, or plus equals dp, but every single thing in dp has to be multiplied by the current size, right? So times 32, or chunk size, divided by the level. Right, so level 0, it will be multiplied by 32. If it's level 1, multiplied by 16, so on and so forth. Right, so I suppose even we could shift it in by 5. Shift it in by level. Totally possible. No, wait, because dp is a vector, so no, never mind. Multiply by 32. Shift it in by some level. Yeah, right, and then plus equals t times 0, so that is totally fine. Remember someone taught me... oh wait, it's not read yet in my OBS. It's so annoying. Like I see chat on my phone, which is why I have my phone up all the time, way earlier than I actually see it in OBS. But yeah, I remember someone thought my var name wasn't descriptive, so I named it value of the previous position of the value that I am assigning here in this function and in other places, like out on the line before or something. Yeah, just make it 5 lines long. It's fine. Totally fine. And then plus equals t times 0. Okay, so that is okay. Yeah. Yeah, so I guess we can say here while ir plus.x equals smaller than 32 and ir plus.y.x equals greater or equal to 0 and ir plus.y is smaller than 32 and ir plus.y greater or equal to 0 and ir plus.z smaller than 32 and then ir plus.z greater than 0 or equal to 0. So if our ir plus, and I guess we should just call this like our integer relative position, but I suppose it's like our with respect to the chunk, like our voxel position. Maybe I should call it that, like the position for our voxel position. Oh, no. And the voxel position has to always be between 0 and 32. If it is not, then we have progressed the chunk, and we should go out of this loop and progress the chunk here. Right, so that makes sense. If it is empty. If it is not empty, then of course I have to check if level is equal to 5, which is our greatest level, right? Then I just have to check the actual color. And so now we do color equals our current voxel chunk, this one, and then x, y, z, which will then be v+.x, v+.y, v+.z. I think you can do a right click on the change symbol name instead of renaming in Ctrl+C, Ctrl+V. Oh, yeah, no, it's, I mean, probably true. There are so many shortcuts that I just never use for whatever reason. And then if... I guess I can just check this, right? So then if color still 0, then I want to progress. So then I want to intersect anyway. You know, I think I should actually just do this, right? So if the chunk is empty, or is not empty, then I want to set the color. Actually, I want... Go back. I do want to check the level. Yeah. Expression is always false. Yeah, I know I will update level soon. If color is still 0, or if color is now not equal to 0 anymore, then I want to break. And we will break out of everything. Otherwise, I just want to continue here. I just want to actually just do this stuff. I just want to progress through everything. Else though, if our level is not yet the finest level, I want to do ++ level. And then I also have to change my relative position or my position. No, I don't think I have to change anything. I just need to update my level. Is it that simple? I'm going to remove this because this is truly useful, or truly useless now. Is it this simple? With our relative position. Oh yeah, our relative position will actually be... Are we even using this? Oh yes, we're using that here. So the relative position I should probably just calculate dynamically, because we're not really using it anymore. var ++ or ++ var. ++ var actually. Because var ++, so if I did level ++, that would basically be the same as doing the following. Just make a var temp equals level. Then it would like use temp for whatever. And then it would say level plus equals 1 here. Then it would use temp for whatever. Something like this. So you actually make an extra variable and then use that for whatever function or whatever thing you're using it in. So in here, of course, it will get optimized out. It doesn't matter. But if you do something like if some func of like I++, then it will make a copy of I, use that in the function, and update I. So it's not great. If you're using ++ level, it will just do it in place, and there is no duplicate variable. So it's nice. Oftentimes, if you make an array, like if I equals 0, I smaller than 5, I++, the compiler... Oh, I did if 4. The compiler will just optimize this I++ to ++i automatically for you. So you usually just don't worry about it. Okay, so I should get a relative position here myself. Do that. Relative position equals new, and then our current position. And I don't even want to do this anymore, I don't think. Current position. Or maybe I do actually. Wait, if I do this, I get my current chunk position. And then what I do, so I can divide that by my current level. +1. No, or 5 minus my level, I suppose. So if level equals 0, then I can divide it by 5. Shift it out by 5. Right, so 32 will become whatever. So I guess it's divided by 32 minus level shifted in by 5. That's what it should be now. Pretty sure So the position.x, which may be 247.73 to whatever. Then we get rid of whatever 32 multiple we are. Right. So that's fine. Then we get something like 27.372. And then we divide it by 32 at first, right? For level 0. We just divide that by 32, which will give us either 0 or 1. Or no, it will give us a value between 0 and 1. Or between the entire chunk, which is great. But then we can do minus level shifted in by 5. So in the first one it is minus 2, which isn't great. Of course, it should be then just divided by 2. Yeah, like this. So I can multiply this by level shifted in by 5. Yeah, so do this, then multiply this by level shifted in by 5. Then divide it by 32. Yeah, I think that will do it. It's a bit messy, but I think it will do it. Yeah, there's definitely a way to do this faster. But we have like 5 minutes. And I kind of want to just test this out, so I'm not going to bother thinking about this too much. I might even, thinking about it, I might just look at this line and just make a little change tomorrow in the afternoon or something before we start the stream. I'll tell you about it, of course. Oh, this should be Z. There we go. It should be our relative position, and in there, and then alpha T, and then this, and then this. Yeah. Honestly, I'm thinking that this might actually work. Yeah, that's insane. That's insane. Okay. Should we just try it? I think we just try it. Oh boy, this is going to be extremely interesting to see. It looks fast though. Like, you saw how many lines we used to have and how complicated things were. This is actually quite elegant, I feel like. Okay, let's go. Very excited to see like anything, but probably we're not going to see anything. But yeah, exactly. I was wondering if we were going to get an error. Out of range exception. Okay, so we do actually get an out of range here. So it's x shifted out by 4, and x can be 16. Right, so 16 divided by 16, which should be fine. That's 1. Plus y shifted out by 3, so divided by 8 is 2. And this one divided by, yeah, so that's 4. That's 3. And that's 1. So this is 8. Oh, and the whole thing is only 8 in size. Right. I thought we kind of did this. And I thought it kind of made sense. Right. Oh, do we need like the 1 shifted over by this much? Because then it will be... No, not at all. It should be between 0 and 8, right? Like this is between 0 and 8. So why wouldn't this be? This thing was 24. Yeah, it should be able to do that. Look at it again. So if we have between 0 and 8, I guess I never wrote that one down, but if we have between 0 and 8, we have x divided by 4, right? Right, because x can be between 0 and 32. Oh, but then it can only be between 0 and... X can be between 0 and 2, right. So then we need to divide by 16. Plus y divided by 16, but then also multiplied by 2. In total. plus z divided by 16, but then also multiplied by 4. So this is just x by 4 plus y by 3 plus z by 2. So I actually really don't see the problem. Right, if now if everything is now 31, right, if everything is 31, then shift it out by 4 is, let's see, so 31 is just 5, 1, so this will just be 1. This will be 3. And this will be 8. Yeah, I'm thinking that might be the issue. It's not 8, it's 7 actually, but still. So this can get to 12, which is not 8, as you may have noticed. Right. If we have a little cube, I want to do this quickly because then we can still test it out and hopefully get something nice here. So if we get this cube right, then we split it up into 8 parts. Like x goes from 0 to 2, y goes from 0 to 2, and z goes from 0 to 2. Right. So usually what you do is you just have x plus 2 times y plus 4 times z now. And then this will be, well, 0 or 1. This will be 0 or 1, and this will be 0 or 1. If everything is 1, this will be 1 plus 2 plus 4, which is 7, which is exactly right. Now, if we do this, z divided by 16, that will indeed be between 0 and 1. Same thing here, same thing here. So if we do x divided by 16 plus 2 times y divided by 16 plus 4 times z divided by 16, then I suppose this will be still x divided by 16, which is actually the same as dividing out by 4. That is still correct. 2 times that, so that will be y divided by 8, which is definitely y just shifted out by 3. And this will be z divided by 4, which is definitely z shifted by 2. This one should only be able to get to be 4, but if I do this, and I do in 32, 32 divided by 4, yeah. 32 is 1, 1, 1, 1, 1. If I shift that out by 2, these go away. So I have these left. Yeah, but that will be 7. Yeah, not 4. So you need to shift it by 1 more. Right? If I have 1, 1, 1, 1, 1 for x, and I shift out 4, I'll have just 1 left, which is 1, which is fine. Yeah, and then for y, 1, 1, 1, 1, 1, shift out 3, which will have 1, 1 left. Which is 3, which is right? No, because that one can be 1, this one can be 2, this one can be 7. Oh. Right, I need to AND it as well, don't I? Because this bit is 4. Yeah, right. So I need to AND it as well. Need to AND it by the biggest bit. So it should be x4 and then AND 1 plus y3 and then AND 3 and then z2 and 7. Yeah, that's it. That's it. Okay. So this should be this. Of course, everything is affected, so might as well. and 1. Which should be the same everywhere. No, I don't think so, actually. It's not the same everywhere. And 3. And here again. Oh, that's bad. And an 7. Here I already had ants. Yeah, just a bit. 3 and 7. For this one, it is shifted in by 3 was 3. Shifted in by 1. I'm sure I'm going to have to recheck all of these, don't I? Like, what pattern is in here? So the other one had x divided by 8, i.e. x shifted in by 3. Right. But then I need a value between 0 and 64 now. So that means that we can have bigger values. So in here I can AND 3, so this will be 2. The other one I can AND even more. You're going to need something like Teardown or Minecraft, or do you have a goal? Yeah, well, that is a good question. I'm not entirely sure what I want to do exactly with it yet, but, well, I want to make an engine with it, right? So in the end, we should be able to make basically anything with it. But I was definitely imagining more like a tycoon type of game, where you have a top-down view. So maybe more like Teardown than like Minecraft, I guess. But even more far removed, I guess. You know, in Roller Coaster Tycoon, Teardown is a bit more to the ground, I guess, than because it's more like third person, right? But in Roller Coaster Tycoon, you're in like God mode, something like that. So that is the view that I'm really going for, something like that. But having a first person view and being able to walk through everything, I have seen this awesome tech demo about a guy who just made this this voxel engine with all sorts of nature and stuff, and it's just insanely beautiful. If I could ever make something like that, then I would definitely want first person view as well, that you can walk through it. But we'll see. So this can be 2, right? We have that. Then we had y shift in by 1. So if we then do an AND of the biggest possible value, which will be, let's see, so that'll be 16, so it'll be 15, is that correct? 7 and then 15, yeah. And then z shifted in by 1, which will be 63, so this will be too big, no? Oh no, wait, that's actually not true. So just like here, 7 is too big. You have to AND it by their actual thing. Yeah. Okay. So this actually still holds true. This has to be AND 3. This has to be AND by 1. It'll be 16, so it'll be 15. And this will be AND 63. And then by 2, that will be 7. Yeah. By 1 is 63, and then by 4 is 255. And the same thing has to happen here as well, when we are reading it out. Oh, and of course, the same thing has to happen here. So let's do this map 2 first. Have U, and then have U. This map 3. There we go. And then this map 4. And here we are. This map 4. That was a mistake. I got thoroughly confused there for a second. Okay, there you go. Let's try that again. Oh, no, we're still getting in out of range here. So this is 1. This is 3. And this is 4. This is 3? Really? Oh, yeah, this has to be end 2, not end 3. Yeah. This one also, end 2. End 2, end 2, not end 3. End 2, end 2. Try that again. Still index out of range. It's 1, there's 2, there's 5. It's not correct. Oh, 7 is also the issue, right? So if we have... I need to get my bit to decimal going. Binary... the decimal converter. Or actually just the other one. The other one around. No? Binary to decimal, yeah. So if we have... just 1 0, that should be 2, right? 1 0 0 is 4, right? Oh, so it's actually just all the powers of 2. Right, so this is 4. Let's just recreate these all in here. So this should be 4. And this is just 2 to the... yeah, so that's 2. This is 8. Right. This should be 32. This is again 4. This is again 32. And this is 128. Okay. And then copy paste this everywhere. It is good to see that at the very least everything seems to be used. So that's promising. Yeah, let's see. Here we go. Try that again. That is working better. 1 gig of memory, that is the same as what it used to be. I'm guessing that we're stuck in some loop somewhere, because this ain't looking too great. Right. So where are we right now? Yes, we are definitely stuck in a loop. That much is for sure. What is the current position here? That is not very far. Good to know. What is T here? There is no T yet. Let's go here. What is T here? T is still 0. Interesting. What is level? Level is also 0. So there's definitely 1 shifted in by 5, which should give us... evaluate doesn't give it, but it should give us 32. The direction is fine. The relative position is also fine. Even if it is 0, 0, 0. Pulse.x is 0.5, but then we do like minus 0. Wait, shouldn't that be 0.5? Oh, and then multiplied by 0. Oh. Hold up. That might do it. Yeah, so we have no relative position at all. This should be plus level plus 1, I guess. So this should be 1. Then the next time should be more than that. Right, it's going to get to 2 shifted in by 5, and it will be 3 shifted in by 5. Thinking that this might not be entirely correct. That's a shame. Let's try that again. I guess we do really have to make a proper RPOS then here. New vector 3. So, right, so our relative position is basically our current position, right? But then we have to subtract our integer position from it. Our voxel position. Well, I think even our voxel position doesn't quite do it. So the relative position of our level. So if our level is 0, we want to divide everything in 32s. If we are in level 1, we want to divide everything in 16s, but then we also want to AND it and thereby kind of bind it to the, you know, like the first 2 in a chunk. Right, so we can do minus. No, not necessarily chunk pos. How do we calculate chunk pos even? Why don't we do this? Why don't we have this? Oh, that does of course like that. Yeah. Minus this though. Minus this thing. This will be our offset x, but then done like that, so we still have like 5 minus level. So then if our level goes up, we want the bit shifted out less, so we get bigger areas. Should have plus, I guess. No, because if level is 5, then we don't want to shift it out at all, and then we just have 1s. And now we have to AND this. Right, now we have to AND this by our level. No. Something like this. So, first of all, we AND this by 32. Right, so then everything will be between 0 and 32. Otherwise, we have to AND it by 16. That's not true. Then I want to AND it by 2. Like, now I can... Right, let's go back to the drawing board, boys. So our relative x position is our actual x position. Right, if we have something like this, our actual x position, but then minus this offset x. Right, and this offset x is very strongly defined by what size we are, right? Or what level we are. So if our little voxels are actual voxel sizes, then we need to get so the actual x divided by our voxel sizes. Right, so that will be our actual x index. Then we floor this. Yes, then we floor this and multiply that by 32 again. So let's say we have this. So it's like the remainder, right? It's like the remainder. So it's not quite like that. It's a quarter past past 10. My brain is definitely breaking down. Gotta go. Expect me to require a recap, of course. That is not an issue. Have a good evening. And hope to see you tomorrow. Yeah, I probably should go soon too. Oh, my brain, my poor brain. So I should subtract this, which is x divided by 32, and then round it. Isn't it just already enough? It's already enough, right? So this is just x minus x, but then divided by whatever, this time by 16, and then we'll get the 16th like extra positions here. or not. Right, so if x equals 32, then this will just be 32 minus 2. Right, so that doesn't make any sense. Because it should give me exactly 0. If we do it times 16, then that will work. If I have then 33, this... Oh no, that does actually work. Because this rounded down will still be 2. So minus 32. Yeah, no, so I should just... Sometimes it's so simple, dudes. Sometimes it's so simple. Don't do what I do. Anyway. Vector 3. And then we need the position.x. And then we need chunk pos. And then in by 5? Should we go out by 5? Oh yeah, chunk pos divided by... Okay, yeah, but I don't actually want to use chunk pos. Where am I? Here. I want to use the actual pos, but then moved in by 5. This should of course be the int of the math. f.floor. Like this. Then in by 5. Yeah. And then 5. And 5 is of course not just any 5, that is 5 minus level. And then here as well, 5 minus level. And I feel like 5 minus level is such a common thing that maybe I should just store it somewhere. I'm not sure. At the very least, this thing can go. Here we are. And this thing is absolutely huge. Okay. Down here we have Y. Y. It's Z. Z. There we go. Now let's check this out. I do believe we are still going to get into a little cycle here. Yeah, let's set a breakpoint right there. Right, so T is still 0 probably, yeah, because that was of course still a problem. Our pos is now way better. So that's awesome. C is 0, but the rest is 24. I'm not entirely sure why, but sure. Like this is 56. So that sounds okay. Y is minus 32, yeah, so that should actually be minus 1 here. Oh, yeah, Y is 0 then, yeah, exactly. And Z is... yeah, something like that. Okay. Sounds good, but then intersect always returns 0. Tmax X, Tmax Z, Tmax Y, Tmax Z. Continue. Never ever gets there. Okay, let's just do this. So Tmax Y is just 0. Oh. Tmax Y is the smallest, of course. Oh yeah, and then we do actually get a unit Y. In a -1 direction, so what is then entirely the problem? Right, so T is 0, so you won't actually move anywhere. What's my direction? Yeah, okay, so that makes sense. Then we should also update our VPOS. Do we not actually do anything with VPOS? Because then in the next iteration it will just use the same RPOS. Dear. Right. Right. Where is VPOS? It's right here. What do we actually do with VPOS? Oh, if... Oh, right. So vpos is the actual. Why is this now -1? Because this is times 32, then shifted out by 0. So that should just be 32, right? And -10 times 32. This should be minus 32 now, but it isn't. Why? Why? I don't understand. Like, does this trigger? Like, do we actually continue here? Not really. Do we have like a different chunk position now? No, not really. So this should be false. Oh, right. This is then false. That's awesome. But we never update our chunk position. Right. Right. Okay, that kind of makes sense. So I suppose what we should do then is we should do the chunk pos plus equals vpos divided by 32. No? Is that not going to work? So vpos divided by 32. Oh. Wait, vpos is actually not updated? How does this even work? So vpos is -1. Oh, it's divided by 32, it's -1. Okay, so then when we update... No, vpos is -1. Guys, you know what? I have a promise. I have one huge promise. We are this close to actually finishing it tonight, but it's getting too late. My brain isn't working anymore. Things are happening. I have to debug some stuff. It ain't gonna work. This is not gonna happen. But so, tomorrow, right? Every afternoon or every evening from 8 p.m. CEST to 10 p.m. CEST. And we are a good half hour past our time here. So that is why I have a very good reason for ending at 10 p.m. So, we are going to end the stream right here. And then tomorrow we will finish all of this. And I very much hope that we can do that in like the first 15 minutes. That would be very nice. And then we can actually do some path tracing. Or some ray marching, I mean. So, hope to see you all there. Hope you all will have a wonderful evening as well, of course. And yeah. Hope to see you then. Okay. Bye bye everyone.